Hi everybody. Today I am going to discuss about the formation of plastic hinges in a propped cantilever. Normally, the formation of plastic hinges in a statically determinate beam it means it produces large and increasing deformation which ultimately result in failure with no increase in load. But in a statical indeterminate system like this one, the formation of a single plastic hinge does not necessarily means collapse. So to reach up to plastic hinges formations, first we need to calculate reactions RB, then to draw a bending moment diagram to see the bending moment at different positions. So to get that, first we have to find the deflections at this point B due to this load P. As well, we need to find again deflection at B due to the reactions here RB. Here I am taking a free body diagram having two reactions RA and RB and a concentrated moment MA because this is a fixed support. Now to find these RA, RB and MA, we need some equations. So how to get those equations? Applying the equations of equilibrium, summation Fy equal to 0, I mean summation of vertical force is equal to 0, so we easily can write these vertical force RA, RB equal to this P, and easily we can write RA equal to P minus RB. So this is one equations. We need another equations, again applying equations of equilibrium, summation of moment equal to 0, here summation of MA because this moment is about this A. So MA will come directly from here because it is concentrated moment, but in case of load we have to multiply it by distance, so RB multiplied by L minus P multiplied by L by 2. So we got the equation. From this we can find MA equal to this. So this is our second equations. Now in the next slide we will see how to find the deflections at B considering the concentrated load P. Again we will find the deflections at B considering these reactions RB. Ultimately we need to find RB, I mean reactions, then we need to find the moment MA and MC. That is our target. After that we can see how these plastic hinges forms. So let's move in the next slide. As I told, I am considering only concentrated load P which is at the midspan acting at this point, This is the deflection curve. Here it is showing the deflection value del B1. So we need to find this. So to do this, to find this, we can use double integration method or moment area methods. But here I am using moment area methods. In this method, procedure is we have to get first moment diagram. So this is the moment diagram for this load P, because P multiplied by L by 2, it will give me the ordinate or the height of this triangle PL by 2, and we know the base is L by 2. So easily we can find the area half height into base equal to PL square by 8. Because we are using moment area method. So we are finding area. Now we have to find the distance of this center of gravity of this bending moment diagram up to this B. So how to get that? From here to up to this point, it is 2/3 of L by 2. And from here to here, it is L by 2. So look at 2/3 L by 2 multiplied by L minus L by 2. I have written in this format because if it would not be equal, suppose if it is here A and B, then of course for this distance I would have to write L minus A. From that point of view, I wrote here L minus L by 2. So this is L by 2, this is L by 3, adding these two I got 5, L by 6. This is the distance x bar from this centroid or center of gravity of this moment diagram up to this B. Now we have to use formula, moment area method. So formula is to find the deflections del B1, A multiplied by x bar divided by EI. So we are putting this area and x bar value, easily we get this. So this is the value for these deflections. Now we have to find same position, the deflection, considering reactions. So we'll see it in the next slide. So drawing this deflection curve, I am getting here deflection del B2. Now here I am drawing the bending moment diagram like previous slides. I mean, we have to get the area of this. So bending moment diagram, here the ordinate or the height will be these reactions multiplied by this L. So it will be RBL. So easily we can find the area, half into height multiplied by this base is L. So RBL square by 2. Now we need to find the distance x bar from here to here. So it is 2/3 L. Now using the formula for moment area method, AX by divided by EI, putting the area x bar, we get this RBL cube by 3 EI. So we got these deflections. So in the next slide, we'll see how to find this RB using the value for del B2 and del B1. So to get that, we have to use equation of compatibility because del B basically equal to 0. So del B1 minus del B2, it will be equal to 0. So value of del B1, del B2, we have to use this equal to 0 and bring this at right hand side. We can find RB. It is 5p by 16. And easily we can find Ra also because we know applying the equation of equilibrium, summation of vertical force is equal to 0. So Ra will be P minus of Rb. So we get 11p by 16. So we got two reactions at A and B. And this midpoint actually it is C. I forgot to write here C. This is C. So already you have seen Ra and Rb. So using those Ra and Rb, we can draw the shear force diagram. And here there is a jump because due to this concentrated load. Now our target is to find the moment. So we have to apply equation of equilibrium. And these equations already we have seen. This Ma is concentrated moment and Rb into L. We know Rb into L. L minus P into L by 2 because we are taking moment about A. Already here written Ma. So how to find Ma? Taking all this in the right hand side. And we know the Rb is 5p by 16. This is the value we now just put because in previous slide we got value of Rb. So what we are getting at an end for Ma? We get 3pl by 16. So this is the value for Ma. Now to find MC, what you will do? This Rb multiplied by this L by 2, we get MC. We already know Rb, we used it here. So 5p by 16 multiplied by L by 2, we got 5pl by 32. So we know Ma, we know MC. So in the next slide, we will use directly this value. So here at an end, we reached to find the how plastic hinges are formed. So this is already we just drew this in previous slide. It is elastic bending moment diagram and I have put the value 3pl by 16, 5pl by 32. In previous slide we got these two. Now if the value of this P, because this P only it creates the elastic bending moment diagram. Now to get the bending moment diagram at collapse, we have to increase this load. So first we are increasing P. So if the value P is increased, a plastic hinge will form first at A. Why? Because out of these two values, this 3 PL by 16 greater than 5 PL by 32. So the plastic hinge will form first at A if we increase the load P. But formation of this hinge does not mean that the beam will collapse, because already I told this is a statically indeterminate system. So formation of first hinge or formation of a single plastic hinge does not necessarily mean collapse. Instead, it will behave as a statically determinate beam with a point load at C. So this is the hinge, and at this point this load is acting. So in this situation, this beam, it behaves as a statically determinate beam with this concentrated load. And as we know already, this hinge is already, formation is already happened. So here we can consider this plastic moment MP, because already we know this plastic hinge already it is formed. So the moment here will be MP. Now further increase this P will eventually result in the formation of the second plastic hinge at this position C. So in the same way, we can say as this hinge already it is formed, so the moment here will be MP also, plastic moment. So after formation of this second hinge, the beam, it will behave as a mechanism. This is very important point. And failure occurs with no further increase in loads. So this bending moment diagram, this one, so it has value MP, it is actually minus at A, and MP at C it is with plus. Now if we compare these two, this is with elastic deformation and this is with collapse. Two scenarios. This is with elastic deformations, but this moment diagram it is with collapse. So we can say that a redistribution of bending moment has occurred. Right now we can say that. So what we can say also, elastic bending moment diagram, it has a maximum moment here at A. But after the formation of plastic hinge at A, the bending moment remains constant while the bending moment at C increases until the second plastic hinge forms. We can conclude that. Also, we can say that this redistribution of moments, because seeing these two, we understood that redistributions happened. So this redistribution of moments tends to increase the ultimate strength of these statically indeterminate structure, since failure at one section leads to other portion of the structures supporting additional loads. Already we have seen all these activities. Now we may determine the ultimate load. We already got the plastic moment in this diagram, so we can determine the ultimate load by statics. How to do that? Let's see. We can write, because this is negative moments, this way, and just we see all the equations. So now if we start here, say first I got this equation, hence MP equal to, we can write easily like this. Now considering the equilibrium length of CB, we obtain this, because RB multiplied by L by 2, we get this MP. And this MP at this position at A, we got equation as PU multiplied by L by 2. This PU, we are using U because this is ultimate load, because already we got the plastic moment. That is how we must use the PU. So PU multiplied by L by 2, it is here, and RB multiplied by L, from here RB multiplied by L, all are about A. So we get this equation. As well we got MP equal to RB multiplied by L by 2 for these positions, MP. Now eliminating RB. Suppose if we eliminate RB, means I can find here RB means 2 MP by L. So I can put this RB position 2 MP by L. So easily from here you can see LL cancel, 2 MP. If we bring it here, it will be 3 MP multiplied by 2, it will be 6 MP divided by this L, it will be 6 MP by L. So that is the ultimate load. So I think that's all for today. Thanks for watching.